Hello everyone, I am Pranav, one of the members of LLB School. On behalf of LLB School and CPMB TNIU, I welcome everyone to the LLB webinar series. We have been conducting a series of webinars on various topics in the recent times. Today, we are going to have an interesting session on molecular dynamics by Dr. Girinath Pillai. Dr. Girinath, Dr. Girinath, something is echoing. 1 second, sorry. Dr. Girinath completed his PhD from the University of Florida in the area of computer-aided lead design. He has a very rich experience over 15 years in the field of computational chemistry and bioinformatics. Also, he is the founder and the chief scientific officer of Zastra Innovations, a Bangalore-based computational chemistry laboratory providing software solutions to computer-aided design throughout India. So let's welcome him and he will take over the session in few minutes. And before that, I would like to give you few instructions which needs to be followed. Sir, can you change the slide one side?
Sure.
Yeah. Participants are kindly requested to keep their webcam and mute, webcam off and their audio mute, and try to note down your questions. And or you can post at the chat box. The questions will be answered at the end of the sessions. If you have any, if you want to ask question, you can use the raise hand option. And don't forget to send your feedback to our Telegram channel. Sir, you can take over the session.
Thank you. So thank you so much, Mahesh, and I also would like to thank Ajay, who introduced my student, who also introduced to your group. So it is really engaging, and I can see many are getting useful support through your group. So thank you so much for this platform. And I also want to add on, I am currently working on aging related aspects. And a few we already published again on the scenario. I call it as a mechanistic drug designing rather than just docking, because we see everywhere it's a docking and bed lab experiments, but it is way beyond that if you want something done in silico to be on the table. So, keeping all that in mind, so today we will be more focusing on molecular dynamics on a beginner's level, but a detailed overview. Because most of the time we work on tutorials. But when you work on tutorials, we are very much focused on, for example, lysosome in water, very, very famous tutorial for Gromax. So everyone focuses on that particular aspects. But when we try to make any changes, or if you want to tweak something, or your problem statement is something similar but different system than what is considered here, then you end up with issues. So we need to have a better understanding of science behind it, where to use, what to use, when to use. So today we will be only looking at what is the definitions, how, why, what. That's all. Now, how to apply, where to apply, and what are the parameters? Of course, I'm thinking of a follow-up session, not yet done because many requests have come. Like I have to more go detail into specifics, so that we will work on it. But today it will be a bit lengthy session. I have around 48 slides. It might take to 1.5 hour or 1 hour 45 minutes, depends. I have another meeting at 8, but I'm good. We have a good amount of time. If you wanted to contact me, any email address, any social media, it's the same ID, it's Giri Bio. So moving forward, we don't want to compare any tools of to discuss about the working of any tools here. So kindly refer to only open access, and all are my personal opinion and does not have any connections with my employer, employee, or others. The slides contain content, pictures, and videos taken from several websites, articles, lectures, tutorials, and and their respective authors own the copyrights. And all the references are given in slide number 46. That is my last slide. So there are 46 slides. So this slide is already available in my SlideShare. So if anyone wants to look at the slides, you can. And a few other sessions I was doing. And if you wanted to do Gromax, using Gromax in Jupyter, where all the commands will be there, You need to just execute and make changes on your parameter file. That's all you have to do. But otherwise, everything is there. Why? Because most of the time we look at something and then execute the command, bit difficult because you might make mistakes on spacing and syntaxes. But everything is taken care. Only thing you have to look at only the parameters which suits your system. Anyway, what to expect today? So, like as I already told you, how MD is performed, what are the force fields, what are the steps, applications, limitations, why it is computationally intensive, and what are the available resources available. Now, let me tell you, molecular dynamics, all the softwares are free of cost for academics. You need not any penny. Only restriction is that you have more flexibility when you work on Linux or Mac. For Windows, there are very limited resources, which we will discuss anyway. So coming to molecular dynamics, it's mimicking what the atoms do in the real life. Also assumes in a given potential energy function. So we talk in all terms of energy function as well as movement of atoms and molecules. The change of positions. That's what we look at more in molecular dynamics. And the first time molecular dynamics simulation was carried out on a simplified protein folding during the year 1975. And on biological process, it was in 1976. So you have to imagine what kind of computing resources was available during that time, and still they were able to manage to do molecular, not so much advanced like what we do now, but they were still able to simulate it. The key properties in MD is that in real life, in an MD simulation, atoms are in constant motion. So they will not go to an energy minimum and stay there. So it will be always on a constant motion. Enough time, the simulation samples a Boltzmann distribution. So it is a probability of observing a particular arrangement of atoms in a function of potential energy. So keep in mind here all we talk about in the terms of energy when depending upon time, acceleration, velocity, and many more factors. I'll be discussing in the next few slides. And this is not only the way to explore the energy surface, but it is pretty effective way to do so. So now what is Boltzmann distribution? As I already told you that it is probability of distribution or probability measure that gives the probability that a system will be in a certain state as function of state's energy and the temperature of the system. So we will also have different situations where we parameterize them accordingly. The mechanics of molecular dynamics, when each atom AI is being considered as a particle with mass Mi and charge Qi, that's where the Newton's second law of motion is applied, where F is equal to m into a. The acceleration of the atom at time t can be also calculated. When you try to check with velocity, acceleration is the derivative of velocity. And when you look at the position, velocity is a derivative of position. So this is how you derive them. Therefore, the position of atom at a particular t, where the change in time also can be calculated. That's the mechanism. So the second law states that acceleration of an object is dependent upon two variables, the net force acting upon the object and the mass of the object. But when talking about MD in energy terms, we always think the total energy should be conserved. Now, the total energy is the potential plus the kinetic. So there will be shift of energies happening, but the total energy will be maintained. The potential and the kinetic gets fluctuated as the state changes. In atomic arrangements with lower potential energy, atoms moves much faster. But in practice, total energy tends to grow slowly with time due to the numerical errors. That's where we call it as rounding errors. In many simulation, one adds a mechanism to keep the temperature roughly constant. That's where we use call as a thermostat. So there are certain algorithms to maintain this temperature. Those I will be mentioning in my later slides. Thermostats will dampen the increase in the energy over time, and the surrounding atoms will try to absorb energy from the system if the system tries to increase in energy. So everything is controlled there. So that's where we call it as constraints are being assigned here. So keeping all these constraints like acceleration, position, velocity, time, energy constraints. So how we can perform this MD? A molecule, a biomolecule or macromolecule, what we call it as proteins, DNA, RNA, etc., contains atoms, covalent bonds, and each atoms are considered as particle and bonds being considered as a flexible spring. So the size of the particle can be defined by van der Waals radii. and strength of the spring is determined by strength of the bond. So if you consider carbon atom, the size of the carbon atom will be larger than hydrogen atom, smaller than oxygen. And when you talk about bonds, double bonds will be smaller than single bond, but larger than triple bond. But when you talk in terms of the strength of the bond, the double bonds are stronger than the triple bond, which is weaker. So the electrostatic interaction also plays a vital role due to the high charge density on the particle. Hence, appropriate charges are assigned on each one of them. So that's where we have to, what we say, ionization. So we have to make a neutralize the system before minimization. All those steps are there, which I will be discussing in the next slides. Using these details, we determine the potential energy from mathematical equation and with a combination of parameter. This parameter is the bread and butter for molecular dynamics. That is very, very important. That's what we call it as molecular mechanics force field, the initial one, but generally we call them as force field. This contains information about van der Waals, bond orders, and many more. If your force field is not appropriate for the system, your whole MD has gone waste. So the choosing the right force field is very important. Now, many of the time people ask, how do we choose a right force field? You have to read, you have to see where it is already being applied, or if it is something new that you're trying out, then the best option would be you try to run a short range calculation, see everything is intact and in proper position. If it is good, then do a long range calculation like nanoseconds or 100 nanoseconds as per the computing power that you have. So choosing the right force field is always a challenge and very critical. Now, what is required to perform MD? A 3D structure of the molecule and the connectivity. It could be a protein, it could be a DNA, RNA, whatever it is, but you need to have the connectivity and the 3D structure. So it can be a primary, secondary, tertiary, and quaternary protein as per your problem statement. The choice of the right force field with element coverage, that's where I told you, you have to, because I have seen in many forums that when they look at a selenium, then gold, they have issues in selecting the right force field. It's always a challenge. Then when you have copper, zinc, magnesium, they are fine because they are commonly available. So when someone generates that force field, then only it is available to you. Otherwise, you have to do parameterization or you have to do a quantum chemical calculation to generate the force field. But again, that is a time-taking process. As a biologist or a chemist, we might not be focusing on parameterization to much extent as a biophysicist or a mathematician might look at. So van der Waals radii, bonding geometry, charges, force constant, these are all the parameters that to be considered along with force field and mathematical formula to calculate potentials and other properties. You need not to worry about formula because I also hate equations and formula. Right now, the softwares and algorithms have the capability to take care of these mathematical formulas. But in earlier days, no, you have to sit and derive them from all these parameters, what you achieve. And they divide the time into discrete time steps and no more than a few femtoseconds. So 1 femtosecond is 10 raised to minus 15 seconds each. So we will talk about this time scale, everything much detail in the coming slides. Now coming to force field, there are different types of interactions. So when you talk about bonded interaction and non-bonded interaction, here bonded interactions are being colored in a kind of a reddish brown and non-bonded in a blue color. So if you see here, these are the covalent bonds. So bond stretching, as I told you, like a spring. So we are talking about bond stretching. So we talk about those parameters or types of interaction. Then dihedrals, right? We are talking about dihedral angles. And then bond angles also, that these between N carbon and carbon bond angle. And these two carbon does not have any covalent bond. They are non-bonded interaction. That's where we call it as van der Waals interaction. And in this case, similarly, Coulomb's interactions also will be there. So these are the types of interactions where force field is going to take care. So what are these? The bonded interactions are interaction potential rises due to the covalent bond properties. And bond stretching and angle bending can be described by Hooke's law. So I'll be giving a pictorial representation, a small animation on what is this bond stretching and bending, all those things. So you'll have a clear clarity there. Now, non-bonded interaction, the potential arises due to non-covalent bond properties. This depends upon Leonard-Jones and Coulomb's potentials. As you can see in this picture, this talks about this as a negative and it's a positive energy atoms, and then you can see a covalent interaction. Similarly, here we are talking about carbon-carbon, where we are talking about van der Waals interaction. These are all non-bonded anyway. Now, the list of force fields available, this is where we most of the time get confused. We have a lot of force fields available. Now, coming to UFF and CFF, up till here, like MMF and MM2, these are the force fields mostly used for small molecules or organic molecules, and then we try to just optimize them. And don't expect that you are going to reach somewhere close to the X-ray crystal structure or geometry. For that, anyway, you have to carry out DFT or higher level CCSD or MP2 calculations on ab initio. So, but MMF 94 and MMX force fields are mostly used for conformational analysis. So, if you want to generate conformations or conformers, so these force fields are used. Universal force field is it has parameters for most of the elements, but accuracy is very well compromised. So UFF is something that is not recommended, but when you go with certain elements which you don't have a very fine-tuned force field, then UFF is the only option that you can go for. Even though if it is a proprietary software or even it is an open software, force field is something challenging for everyone. Now coming with next few of the force fields, these are all free force fields available through GROMACS, NAMD, then Desmond, of course, mostly OPLS, and then AMBER. So these are the main tools that we use for molecular dynamics. So CHARMM can cover proteins, nucleic acids, lipids, small molecules, including AMBER. And GROMOS, again, sugars and small molecules are covered. And OPLS, mostly protein, nucleic acids, and small molecules. Kindly don't get confused between CHARMM force field and the software. So CHARMM, there's a force field that is called CHARMM 22, CHARMM 36. These are all force field. But just CHARMM will be a molecular dynamics package. Similarly, AMBER is also there. AMBER 19, AMBER 20 is a software, but AMBER 98, AMBER 99, FFSB, these are all force fields. So don't get confused with these different similar terms. Now, what are the steps in MD? The preparation of the molecule is the first step, very, very important. You need to know what to be considered in your system and what to be removed. And of course, you need to have a theoretical background on understanding what to be kept. In some cases, you have to remove water molecule. In some cases, you have to keep. In most of the cases, we remove water molecule, and which heteroatoms or other than amino acids to be kept within the system or what to be removed. All those things you have to have a better understanding there. Then we have to define the periodic boundary condition. We have to set constraints. We have to set the boundary for the system to simulate and then solvate it and also ionize it. So solvation, also implicit, explicit conditions on ionization to make it neutral or salt concentrations to be considered. Then we have to do an initialization and equilibrate it. We always wanted to have what to say a good starting point. That is always a biggest what to say rule of thumb when you do any kind of computational calculations on larger system. If you are starting on a very disordered system, it will take too much computing time to get it converged or to get a minima. So we on an initialization is what I meant is minimization. So you have to minimize your system so that your atoms don't overlap. It will be in a right position to start simulating. And equilibration is, which also we will discuss, like ensembles on different velocities, sorry, volume, temperature, pressure. So those things we will look at. And then we do production and simulation at a long range calculation. And at the end, data collection. We want to analyze the trajectories at RMS and RMSD, RMSF, then bond formations and gyrations, etc. So the initiation and basics of MD processes like the interaction mode and initial position. That's what I told you. The initial positions are always important. So you calculate the total force on n atoms, and then you calculate the acceleration of each atom, then you calculate the velocity of each atom, then move all atoms to the new position. That is what is happening when you're doing MD. The process is this. So you start with the initial position, then you make slow changes, you calculate that position's acceleration, velocity, and force, and then make it to new position, again calculate in energy terms. So at each different positions, these terms are being calculated. What is this periodic boundary conditions in that is why we are defining a box. The boundary conditions are required to control the flow of atoms or molecules moving away from the simulation system. The center box always represents the simulation system, and surrounding box are the replica. They are the exact copy. So when you see a molecule is moving from a single box, then it's going out of the boundary, then you see it is again entering. So that's where it is a replica. So whenever an atom leaves the simulation cell, it is replaced by the image which enters from the opposite cell, that is a phase of replica, and entering and keeps the number of atoms in the simulation cell conserved. So this is the understanding we are setting boundaries to in simple terms, and then avoiding the edge effect due to the movement of system during the simulation, as well as the molecule interacts with images in the replica to mimic the bulk phase. So keep in mind, the same protein, if you try to optimize without a periodic boundary condition and with the periodic boundary condition, the situations are different. Here box, I call it as a box in a simple terms. So here the properties that we can understand is the pressure, stress, density, volume, area. So when you solve it, when you define the box, you will be getting to know about all these parameters when you're running any of the simulation programs. Now, what is solvation? Ignoring the solvent, it is leading to major artifacts because it will be in vacuum. As you can see on the right hand side of the slide, the situation will be in the vacuums. But there are situations where water salt ions like sodium chloride, lipids of the cell membrane, or provide a dielectric effect that affects the electrostatic interactions for determining forces. Now, I'm sure that you might be heard of binding energy calculation using MMPBSA, GBSA, all those things. They are all implicit solvation. They are very less accurate. That means those energy values are not that much reliable because it is on an implicit condition. There are plenty of tools available where it can calculate based on PBSA and MMGBSA. So mathematical models to approximate average effects of solvent, and solvent replaced with continuous homogeneous medium of bulk dielectric constant. So here it is a continuum solvation. So they try to get the dielectric constants of the solvent, which is in the implicit condition, and try to do the calculation or derive the properties. On explicit solvation, this is what the different models we have, water models like SPC, SPCE, TIP, 3P, 4P, 5P models available, which we usually use in our protein molecular dynamics in GROMACS or AMB or any others. So they are highly computational expensive but more accurate. Usually assumes periodic boundary condition. In the other implicit, they don't. And actual models of solvent molecules. That's why whenever you're doing a drug discovery project, most of the time, to make our life much easier and make things much quicker, we end up doing docking and its corresponding GBSA or PBSA because you wanted to get the binding energy. But if you want to really be serious and looking into really what is happening, of course those implicit solvation conditions can give you an idea, but explicit solvation is something which is preferred. But you need to have good computers to do that. We will discuss about what computers required for certain kind of calculation. Now coming to ionization, neutralizing a system is carried out for obtaining correct electrostatic values during the simulation. So you have to make it neutral. Otherwise, the electrostatic terms cannot be calculated. That's where under periodic conditions using PME, the system has to be neutral. Addition of ions means the some salt is present. However, this is not equal to the saline condition. And if you want to simulate your system in the presence of a salt, neutralize and achieve the concentration of interest. Now, whatever I'm telling you is theory behind it, but now most of the algorithms are taking care of it. For example, NAMD has an ionization algorithm, which automatically takes care of when you try to neutralize the concentration is also being maintained accordingly. And some proteins in real might be sensitive to the salt concentration. Therefore, ensure the positions of ions is acceptable in the system prior to the simulations. So that is what we have to look at. Just a minute. So that is what we have to look at with the when you're doing ionization. You have a better understanding. And just imagine, it is not only that sodium and chloride you can add. There are many other parameterizations on ionization possible. After the system is being prepared, then as I told you, we wanted to have a initial positions of the atom to get started. So for that we do minimization. So for minimization, we don't do a very long range calculation, we do a short range calculation. So prepare, we want to prepare the system of to have introduced unnatural stress, for example by placing two atoms accidentally too close to each other. But now the algorithms are much more advanced, and they take care of overlapping of atoms and others. But still, result in large forces acting on the particle that would also blow up the system. That happens. Sometimes I could hear from my students that, sir, I simulated, I could see it's all broken apart. What happened to the system? And to solve this problem, an energy minimization is performed in which the system is relaxed to the closest energy minimum. So it is not that whatever given in the tutorial only give that time step. Sometimes when your system is much larger and more complex, you might need to increase the time step, might be required. So you need to have a thorough understanding there. And then we go for the equilibration phase, which is conducted under the ensemble of interest to remove the effects of adding water, ions, and whatever else around some initial solute of interest. Or more generally, remove the possible artifacts of whatever construction is done in whatever system of interest, which may be ordered. That is low entropy and high regularity, or total quantum and therefore unknown reality. So it is a complex state. We wanted to make things right. And we do not want the protein to move significantly during the equilibration phase, so that we restrain it in a harmonic forces to its initial positions. So that's where we give a lot of parameters in the MD equilibration step, what all constraints to be given. I'll be discussing about that in a while. So coming to equilibration, it is a purely statistical mechanics which explains the thermodynamic behavior of a larger system. So even though in most of the MD programs we talk about NVT, NPT, there are many others also like grand canonical, isoenthalpic isobaric, and isothermal isobaric. There are many other equilibration systems available. So, but we will more focus on what is being we are usually seeing, that is microcanonical, that is NV. It changes in the moles, that is the N, and then volume V and the energy. Given the initial positions and velocities, we can calculate all future or the past positions and its corresponding velocities. Coming to canonical, it is NVT, that is the substance that, or the changes in moles is N, the volume V and the temperature T is conserved, and energy of endothermic and exothermic, I hope you know what is endothermic reaction and exothermic reaction process, is exchanged with a thermostat. That's what I told you, there's a constraint or filters that we can keep it intact, so that the energy is being maintained or the temperature is being maintained. Then isothermal isobaric is NPT, where pressure and temperature are conserved, and they are close, very close to lab conditions with ambient temperature and pressure. NPT is somewhere close, very close to the production run and simulation. So most of the time, NPT itself is a simulation also, but in certain conditions, we also extend the calculation. So NVE is to increase the temperature, and then NPT is for production simulation. NV is not at equilibrium. Said microcanonical is not at equilibrium. It tries to check the temperature, pressure, density, and total energy. If everything is stable, it might be at equilibrium state. In most simulation, the system will change a lot in NVE and first period of NPT, and then only it becomes stable. So equilibration. So we did minimization to start with a very good get started positions for the atoms, and then we did NVE to check the stability and all the other parameters like temperature, pressure, density, and total energy intact, and then we simulate it as a production run. And we wait till until it becomes stable. Now, production run or simulation, these are unrestrained production MD runs, nose over thermostat, and Parnell Rahman barostat, of course, for the pressure, was used that they more accurately sample the isothermal isobaric, that is NPT ensembles. They did not use them for equilibration, as they introduced large oscillations around their target values of temperature and pressure. if the system starts far away from equilibrium. That's the reason why we start with NV, make it more stable, and then go for simulating it. The goal of most typical simulation is actually to have equilibrium sampling during production, that is data collection. So whatever data we are collecting should be appropriate and genuine. So in order to achieve that, the system has to reach the stable stage. Now, what are the parameters that we have to consider when you're doing MD simulation? Basically, the size. So when you say, I have a machine which can run 200 nanoseconds per day. Now, the next question is, what is the size of your system? Second, how many, did you do it on cores or CPUs or GPUs? And how many of them did you use? So until you ask these questions, you cannot really understand what that 200 nanoseconds per day did. Now, let's say in my laptop, if I'm doing 5 nanoseconds per day and we say that maybe 20,000 atoms, you are coming and giving me maybe a 30,000 atoms, I cannot do 5 nanoseconds per day. It might be 3 nanoseconds per day. So that is the level of understanding. So the time step, total time duration must be also selected so that the calculation can finish within a reasonable time period. The time is a big factor here, and it will cost you if you don't do it in the right way. So ensembles like NVT, NPT, NV, which we discussed, temperature, pressure, then thermostat, of course, for velocity rescaling, barostat, there are different algorithms and types are available, Langevin and MTK, restraint constraints, again, different algorithms are shades, and short range and long range electrostatics like PME, then time step in femtoseconds, nanoseconds, picoseconds, and it also talks about the duration of MD run. I'll be showing you a calculation how to calculate the time and MD integrator, which is called Verlet. In Gromax, they're using by default Verlet. Of course, we are free to change it. So this is to integrate Newton's equations of motions, which was used by Delmabre in 1791. Now, coming to the last part, what are these trajectories or data collection? The main output from a MD simulation, and it contains coordinates, velocities, and energies of all information that is generated during the simulation of molecular dynamics. Now, what all you get from there? Temperature, pressure, and volume, energy like potential, kinetic, and total, RMS, that is root mean square deviation, as well as fluctuation, secondary structure analysis. I'll show you some examples. Then radius of gyration, hydrogen bond analysis, covariance and cluster analysis like a principal component analysis, then protein ligand interaction studies. When you go for protein ligand interaction study, there are a situation where you do QMMM, like a hybrid condition of simulation. So you do QM on your ligand part and MM on your larger protein part, and then do a hybrid, and then it's a catalytic site analysis, and many more studies will be done on protein ligand interactions. And then free energy surfaces, FEPs, perturbation studies, and many more. Those all data can be taken out from MD trajectories. Now, what is the hierarchy of principal motion and duration of MD? This is something which I spend a bit more time on preparing this particular slide compared to the others. So this is where I'm going to talk about how much time to be given for what kind of calculation, and what kind of computers you require for that particular calculation. So let me start. So first is the bond stretching. The bond stretching interaction, it is helpful to consider how the energy of a bond changes with its length. As you can see, the symmetric stretching and asymmetric stretching, as the picture itself is self-explanatory. Then coming with stretching vibrations. Symmetric stretching, two or more bonds vibrate in and out together. Asymmetric stretching, some bonds are getting shorter and the other not. Then we have hinge bending. Left and right, up and down, one is up and one is down, or vice versa. So binding is the variations of angle of the bond that is caused by vibration. So most of the small molecule force field, or most of the force field, first they try to consider all these parameters during minimization or on a normal equilibration step to correct all the bonds to make it in the right positions. And now, whenever I'm saying, I didn't mention that. So when I say 10 raised to minus 15, so 1 femtosecond is 10 raised to minus 15 seconds. That's what I meant here, if it is getting confused. Picoseconds is 10 raised to minus 12 seconds. 1 nanosecond is 10 raised to minus 9, micro is 10 raised to minus 6. So when you're going for alpha helix folding, secondary structure protein and is a right-handed helix conformation in which every backbone, which is like nitrogen hydrogen group, hydrogen bonds of the backbone of keto group are also being maintained. And then we have beta hairpin folding, where a simple protein structural motif involving two beta strands that look like a hairpin. That is again in milliseconds we are talking about. And then when you're going for a large protein folding, a polypeptide chain that folds to become a biologically active protein in its native 3D structure. And the protein structure is crucial to its function. So there we go on a level of seconds, on a real life, right? But now let me explain in different terms on application side. If I'm going with something with a range of femtoseconds and picoseconds, then it is bond vibrations. That's where we more look at. And side chain rotations within picoseconds and nanoseconds. Then backbone fluctuation. So when you did a homology modeling and you wanted to check the stability of your model structure, the backbone, of course, you do the calculations on nanoseconds. And then a loop motion or gating, again, it's done in between nanoseconds and milli or micro or milliseconds, and ligand binding unbinding events some hundreds of nanoseconds, anyway greater than 100. Collective domain, it's again going with the microseconds. So I have taken this from a few papers. The main ones are here cited here, so others are all there in the 46 slide number. Now let us have an understanding what kind of computers you require to do these calculations. The first one, it requires 1 gigaflops. So the latest laptops will come up with some GPU cards and i7s. Of course, it will cost you a lot, minimum 80K or 70K minimum, so that you will be able to do some simulations on normal nanoseconds like 10 or 20. But again, it's more time. Keep that in mind. So you have a good temperature is being maintained. And when you're going for the next level, like 1 teraflops required, you go for a workstation. And when you go for a 10 teraflops, when you want to do more about helix folding and all in microseconds or between nanoseconds, you go for small clusters. And then if it is 100 teraflops, you go for a larger cluster. But when you go wanted to do milliseconds and seconds in real life, in real time, then you go for petaflops, where it is a data center. So of course, most of them, after whatever I showed you from workstation, most of us individually may not be able to afford it. I understand that is biggest limitation when you're going for molecular dynamics. Until you have a very good computing power, whatever you wanted to achieve, it will be a challenging part for you. In laptop, of course, for learning purpose you can do, but if you want to do something unrealistic, it will be very a tough game. And don't burn your laptop by doing long calculation. So it needs a good temperature maintenance either way. So this is what I want to tell you in this slide, which will give you a brief idea about what is done, where it is done, what is the time, and what kind of facility or requirements is required. Now, GPU is always good, but keep in mind you need a good GPUs, not the normal GPUs. So talking in GPUs, it's preferred that you have NVIDIA. They support CUDA libraries, and most of the molecular dynamics scale, I mean, they are being coded in CUDA, so they do well. So when you have anything similar to like AMD's Radeon GPUs, to be honest with you, so far I don't know is there anything that really supports there. But their high-end cards, of course, they do support on these simulations. So on a normal laptop or desktop cards, I don't think so. But please correct me if you have some latest information. But NVIDIA's, if you have some CUDA cores in there, even if it is a 300 CUDA cores, of course, you can make use of it if it supports CUDA toolkit libraries. That is very important. Why MD is computationally demanding? Because many steps is like millions to trillions. I'll talk about this millions and trillions. Substantial amount of computation at every time step, dominated by non-bonded interaction as they act between every pair of atoms. In a system of n number of atoms, the number of non-bonded terms is proportional to n square. Sorry, it is n to the power 2 power. So can we ignore these interactions beyond atoms separate by more than some fixed cutoff distance? It has some issues, because for van der Waals interaction, it is yes, because these forces fall off quickly with distance, but electrostatics, no, these forces fall off slowly with distances. So that is why MD is computationally very demanding. Now, how to speed up these MD simulation? The first answer is you need to have a very good computers, either CPU or GPU. But otherwise, you can reduce the amount of computation per time step. But that is a call that you have to take. What kind of problem statement is in front of you and what you wanted to achieve. So it is not that simply you can reduce the time step. So you have to have a better understanding there. So fast approximation method for compute electrostatic interactions or method that allow you to evaluate some force field terms every other step. That's just what I told you. So try to run short range calculations to evaluate the force field, evaluate the parameters. If everything goes well, then you go for the larger scale. So you can go for 100 nanosecond, no problem. But if you did 100 nanosecond, the initial step, and then it didn't come as expected, then you wasted a lot of time. Reduce the number of time steps required to simulate a certain amount of physical amount. One can increase the time step several fold by freezing out some very fast motions, that is a certain bond length. These are very much prevailing in surface calculations or membrane calculations. We try to freeze certain areas, but you have to see where you can apply this. Reduce the amount of physical time that must be simulated. A major research area involves making events of interest takes place more quickly in simulation and at low energy confirmation, which states more clearly. I'm not going more deeper there. Parallelizing the simulation across multiple computers, if you have the facility. I know a few of us have access, but not many of them. Redesign computers like GPU or CPU, and there are many more other specialized CPUs like Anton CPUs and many more others, but they're all expensive. So as an individual, we might be easily accessible to CPUs and then go for GPU. So right now, latest laptops, if you go for i5, at least there are four cores are there, four physical cores are there. Older generations, two only, and if it is i7, you can get up to eight. But if you have desktops, if you're planning to build a desktop, you can go for i9. But recently, I built a machine. Personally, I built a machine as an assembled machine. What I did is that I purchased components from the market and build it up. So what I did, I went with a Ryzen 9. So I got a 16 core, built a 16 core physical core and a 32 thread with the 32 GB RAM and a graphics card worth of 38,000 rupees, a decent amount. So I can do kind of 25 nanoseconds per day. But if it is a smaller system, 50 nanoseconds per day. So again, now you know when I say 50 nanoseconds per day, it depends upon the size anyway. So it is up to you how you wanted to scale these things up and how far you wanted to invest on it. Now let's talk about the application. So while you're defining the kinetic properties, that the time-based evolutions of conformation, that is a refinement of protein structure and complex, mostly we do based on the model structure from homology or ab initio. Then stability of protein structure, conformation sampling of small molecules, protein folding, stability of protein ligand interactions, and transport of ions and ligands. And coming to the next, thermodynamics, of course, free energy of binding, FEP, PBSA, GBSA calculations, heat of vaporization, pressure and boiling point. This is more of statistical thermodynamics terms, as I told you, implicit conditions, similar to implicit conditions. Now, where does the ligand or the drug bind and are they stable? This is what the simulation is being done. As you can see the video, the citation is there. It is from Nature 2013. It is done in microseconds anyway. So they're trying to see the simulations where the molecule binds to its receptor and how it changes the binding strength of molecule that binds elsewhere. There's another one more application at the bottom, as I've used the information to modify the molecule such that it has an effect on enriched effect. So here this picture is very interesting. So what it tries to say is the interaction between the ligand and the atom of the specific amino acid throughout the simulation, up to how much percentage of time the interaction between these stayed back. So during throughout the simulation, 96 percentage this interaction was there, but here if you see, this interaction was stable only till 45 percentage. So this also helps you that understanding the stability. So how many of them asked me last time, like, how did you make this picture? It was taken from a paper. It is there in the 46. I'll point out. So what they did is they manually calculated it and they tried to mention this numbers here. So it's nothing like automated process. Then mechanisms of allosteric protein allosteric in MD assimilation, bidirectionality and principles of microscopic reversibility, structural basis of allosteric modulation of a GPCR or mechanism of GPCR activation, mechanism of nucleotide release in heterotrimeric G proteins, mechanosensitive interaction between bacterial adhesins and fibronectin. A bit high level calculations, I should say. So once you get more into deeper into theory and understanding of science, this will have a better under. These are taken from these three papers, whatever content in this slide. I'm not an expert here, so I will not comment too much here. Then coming to functional mechanism, simulations were performed in which a receptor protein transitions spontaneously from its active structure to its inactive structure, like conformational analysis, and then used MD information to explain the mechanism of which drug binds to one end of the receptor, causes the other end of the receptor to change shape, which is to activate. This video actually shows you the simulation on sodium ion channels, so you can see the conformational changes on that. Then process of protein folding, for example, in what order do secondary structure elements form? And but note that short MD is generally not the best way to predict the folded structure. So here you can see how far the protein is forming the secondary structure elements and how much time it will be taking. So it will be showing the details. So N-terminal beta hairpins are forming, and yeah, it is stuck in a non-native strapped state. So this will not happen in a normal 10 nanoseconds. So you need to go beyond or close to microseconds. Non-native contacts break, and now still there is a N-terminus portion. So the clean secondary structure units are now formed at this, and then the third part of the sheet is still missing. So we have to further wait for the simulations, and yeah, you have to watch the N-terminus. So the C terminus slides also into the place, and so that you can see that C terminus forming again. Yeah. So this could be only achieved on a long range simulations. So they locks in with the hydrogen bonds and the side chains, and they yielded a folded structure now. So this is taken from folding at home. This is the protein fold project, and I think they have used NAMD for this simulation. Okay, so now the protein is folded and ready to define the functions. Yes, so the citation is. Now, also MD as a snapshot, the complete molecular dynamics on steps on higher time scale at higher pressure, and then get down the pressure to see what is the stability, and then they define it. So at the temperature of 325 Kelvin, and at different time steps, they're trying to see how far this goes. Sorry, let me check my internet if there's some issue. It seems a bit slow. Mm, okay, I think it's okay now. So you can see that the pressure has gone 9,000 bar, and then they reduced the pressure drop is being done, but still the time is going more than 2,000 nanoseconds. And then now they're doing the protein is the hairpin formation is happening, like what we were discussing previously. Yeah. So the folding step 2, again, now you can see it has reached 5,000 nanoseconds. Yep. At 6,200 nanoseconds, we got the folded state. Unimaginable if you wanted to do it in a laptop. Forget about it. So that is the challenge that we have, but we have to see what kind of problem statements that we have to based on what resources ready hand with here. So now let's discuss about time scales. The simulation has short time steps for numerical stability. That's what one time step is equal to 2 femtoseconds. 2 or less than that is more recommended. So one femtosecond is 10 raised to minus 15 seconds. Now, how can we convert this to nanoseconds? So one time step, I have 2 femtoseconds, and I'm putting 1 crore steps. Okay, so 1 crore into 2 femtoseconds is 2 crore femtoseconds, which is equal to 20,000 picoseconds. Now 1,000 picoseconds is 1 nanosecond. So 20,000 picoseconds is 20 nanoseconds. So in your any simulation program in the parameterization, you have to give the one time step, what is the time, that is 2 femtosecond, and how many steps to be carried out. So when you multiply them, you get to calculate this many nanoseconds. So you are not simply saying that, okay, do calculations for 20 nanoseconds. No, you have to define the time step as well as the steps. Then structural changes in proteins can also take, like as we already saw in the video, as at each nanosecond, microseconds and milliseconds are all longer, the structural changes are taking place in proteins. So it takes more time. Until recently, simulations of 1 microseconds were rare, very true, because it can be done only on large data centers with the load balancing. We cannot do it on a normal cluster too. Advances in computing power have enabled microseconds simulations, but simulation timescales remain still a challenge. So enabling longer timescale simulations an active research area involving algorithmic improvements, parallel computing, GPU or specialized hardware. Another limitation is that, so the previous one which I was telling about timescale is about a limitation. That is what I wanted to emphasize. Other limitation is force field accuracy. Molecular mechanics force field are inherently approximations that we all know. It is not the exact ones. Most of the computational methods are like that. They have improved sustainably over the last decade, but with many still limitations remain. In practice, one needs some experience to know what to trust in a simulation. That is very, very important. That's why I said, even though you followed all what is written in the tutorial, but that might not be trustworthy for your system. It is trustworthy for the system they considered for the tutorial. So you need to have some experience on understanding. So that's where I say a synergism between human expertise and algorithmic efficiency can make wonders. So here force fields, this is taken from a paper, the PLOS One paper. So here force fields with the lower scores are better as assessed by agreement between simulations and experimental data. Even the force fields with scores of 0 are imperfect, however. So you can see that these are FF99, FF03, they are amber force fields, okay? And Charmam, so Charmam 2227 was earlier days. Now you have Charmam 36 also. Even recent version, March 2020, I think it is already there, or 2019, I forgot. 2020, I think. So Charmam 36 also available in the force field. So you can see these force fields are much closer to the experimental data. Now, bond formation and breakage, that is another limitation. So, molecular dynamics more we talk about in biophysical terms or a biophysicist terms, right? But if you want to talk more in the chemistry terms, that's where a little bit limitations on the force field. So, once a protein is created, most of its covalent bond do not break or form during typical function. Same with ligand also. A few covalent bonds do form and break frequently in real life. So like disulfide bonds between cysteines, then acid or basic amino acid residues can lose or gain a that's a proton. But on MD, we cannot. We cannot simulate that because that is a limitation of force field. The limitation of certain force field, low temperatures are not well described. Tunneling of hydrogens are not described. Heat capacity is considered wrong. Chemical reactions are not described. High frequency vibrations are inaccurate. Electronic polarizations are also described implicitly. So we need to have optimization on force field where it can talk in the terms of chemistry, where the bond formation and bond breakage is also being taken care of. Now there are some specialized MD. Now let me tell you, this Langevin dynamics at the end, the bottom, Brownian dynamics is something that we are already using it, which is embedded in whatever dynamics we are trying to do. Now coming to simulated annealing, it's at a different temperature for a fixed duration in a single run using a thermostat. I have seen plenty of publications on simulated annealing. And they also try to avoid the chance of molecule getting blocked at local energy minima. So that is a conformational potential energy barrier. Then TMD, SMD. These are, which I already showed you, where the sodium ion channel and the conformational changes. That is something similar to TMD. So explore conformational path between initial and final conformation of a molecule, opening and closing of ion channels or transporters or large movement of domains in kind. These are TMDs or targeted MD. Then steered MD, it is also similar to TMD, but using a pulling force. So they study the mechanism association or dissociation of ligands with a receptor. REMD is also widely now, I can see many papers are coming up on replica exchange MD, combination of MD with Monte Carlo. This method is capable of overcoming high energy barriers easily and sampling conformational space of protein. So Monte Carlo is something that is gives you very what to say freedom to have a better organized system to doing your MD. So that's why here it says overcoming high energy barriers easily. So these are the capable. So all whatever tools I was discussing, all are capable of doing this. Only thing you need to have a little more deeper understanding of algorithms, parameterization. Algorithm means I don't say coding, scripting. You don't require any coding. You don't require any scripting. You need only to understand what these numbers represents. If I reduce a number, what will happen? If I increase a number, what will happen? What are the keywords? That's all you want. So many of you have a misunderstanding. Coding and scripting to do molecular. No, never. Now I'll talk about some of the resources which are free completely for academic purpose. You need not to pay a penny for that. Because most of the time we get restricted saying that, oh, I don't have money to pay any proprietary software, so how do I go for it? But for MD, none of them you require to pay. So macromolecules, biomolecules, small molecules, you can use Amber. Amber was paid, I think, until last version, but now they made it Amber through Amber tools. It's only for GPU you have to pay. So if someone is really wanted to do a GPU, then you have to pay. But otherwise on CPU you need not pay. So Amber is a very good package. And then GROMACS, of course, everybody loves it and everyone works on it. Even there are some glitches here and there when they work on it. Then NAMD is the only tool that can help you to work on Windows without any other supporting programs. So NAMD directly works on Windows. Then Charmem, Charmem GUI is there, and there is a paid version of Charmem and also free version of Charmem available. And then Desmond. Desmond is completely free for academics. I will tell you details going forward. And then LAMS is something only for solid state and materials. So that is a large scale atomic molecular massively parallel simulator. It's a very famous free package being used by industrialists, many research in the material science or nanoscience area. Very less used and very minimally used in life science or biological systems. So coming to GROMACS, you can go to gromax.org in order to download the software. So now I have to tell you some specific requirements. If you're working on protein ligand interaction studies and if you wanted to really work on MMPBSA, then you have to download only the version 5.1.4 because the MMPBSA code will support only this particular version. But if you're focusing, okay, you're not worried about MMPBSA, but other protein ligand interactions are fine, simulations are fine with me, and you're going to scale it on GPU. 2020.2 version is also recommended. Unfortunately, this does not work in Windows. It is all in Linux and Mac OS 64-bit. You have to extract and compile the package. If you think that I don't know how to compile, there will be dependencies and issues are there. So small marketing from my side. So in my YouTube channel, I have created a Linux for beginners, Linux installation for beginners. So there I have used Linux Mint. So if you are an expert in Linux, of course, you can install Synaptic Manager. Through Synaptic Manager, you can install GROMACS. You need not to do any compiling. Just go there, search for GROMACS, just click on it, install. Very easy. So, but Ubuntu does not have Synaptic Manager, which they had earlier. But you can manually install it. If you still don't want to do that, just install Linux Mint. So in my video, which I have given is Linux Mint. So already it is there. You need to just search for Synaptic Package Manager, then give GROMACS, and not only GROMACS, many other tools can be directly installed without compiling. Yeah, so otherwise, if you think that you want to work only in Windows, yes, you can still do it. You can go to WinMoStar and you can download the SIGWin. But keep in mind, still you're using all Linux commands only. Only thing is you're using Windows. So through Sigwin, you can run GROMACS. But scalability, all issues are there. But for learning purpose, it's always fine. Then you have NAMD software. As I told you, this is the only one which directly works on Windows. Otherwise, Linux, Mac, it supports GPU. GROMACS also supports on GPU. Sorry for the background noise. So you have to register for to download the software here. Then Amber, which I told you, like ambermd.org, so that you can download an Amber, and you have to compile the also the compile the package. So compilation is very important here when you're going for Amber tools. And then you have Desmond. Desmond should be downloaded from D Shaw Research, and it is free only for academics, not for commercials. And then if you are having only CPUs, and this works only on Linux. So if you have only CPUs, then download 2018 version. And if it is a 2019 version, it works only on GPU. Oh, sorry, just a minute. Okay. So as I told you, all these presentations are available in the SlideShare if you want. But if you wanted to use GROMACS like lysosomes in water, so that you can download the Jupyter notebooks available in Zenodo, or you can take it from GitHub. So this will be straight away easy. And I have already done a session on how to perform these calculations straightforward. This is how the Jupyter notebook looks like. So already you have these what to say commands already inbuilt there, and you have to make only changes on the parameterization. And these are the content or references from where I have taken all the content for these slides. Some from papers, some from web sources. So you can also make use of referring to these slides. They have much more detailed explanation than what I have discussed here. So thank you so much for your patience. I hope I was able to finish it in time, like 1 hour. I thought it will go for 1.5 hours, but I think I made it. So a follow-up session can be scheduled if you're interested on how to run GROMACS, but again, using only Jupyter Notebook, because there are many sessions, many videos, many tutorials available on how to run GROMACS on a normal way. So I want to do something different. So you could execute a Jupyter notebook, which is in my GitHub, and run short MD simulation. Use the PDB1 AKI, which is a lysosome, and you can send submit queries or the data to the link given below. That is called in the GitHub. There's issues. So if you have any issues executing the notebook, you can always reach to me. So this will be a small exercise so that you can start playing around. But please understand what each step does and what it makes difference when you do changes in the parameterization. So that's all from me for today. And thank you so much. Over to you, Pranav.
Thank you, Dr. Giri, for giving an brief overview about MD and the softwares available to perform MD simulation. Also, what are the pitfalls and measures we should be considering to run MD simulation? So there are few questions. Shall I read? And then you
Please,
can answer. Yeah.
let me see whether I can see it so that.
Yeah, I'll send you. Yeah, sure, sure. I can forward you. 1 second. So that maybe you can see though. It'll be easy.
Yeah. So let me stop the sharing. Yeah. Now you. It is
Yeah, yeah, I can share the questions. 1 second.
about.
No, I can share in the screen also, not a problem. Yeah.
Okay. Oh, it's in a Word document. Okay.
Yeah, yeah, yeah. No, I just compiled it actually.
Okay. Okay. It's the same thing. Okay.
Yeah, yeah.
What are the criteria to choose force field for the protein or nucleic acids, etc.? I think I already told you that either you have to go through literatures or trial and error. Try to give a force field, do a short range calculation. If everything goes well, good. Otherwise, try with another force field. That's the only way. So mostly you have to understand from the previous where they have applied. But if you don't have anything, then you have to do a trial and error. What is the best combination of parameters that can be applied to boost the duration of MD simulation. Uh, so these are software specific, but I already told you in the limitations on the time scale what to reduce, like time step and others, how to boost your MD simulation. But other specific parameters like cutoff values, which algorithm to be used, all are the software specific. So GROMACS might support some algorithms, but not Desmond. So similarly. What is the recommended time in nanoseconds for backbone fluctuation? I think I already showed in my slide, but what I would recommend is something where close to 50 nanoseconds or barely. People have seen 10 nanoseconds also. So it all depends upon the complexity of your protein. So if it is too complex or if you have done ab initio, then higher the better. But if you are doing a homology with a more similarity with your template, even 10 is also fine, 10 or 20 is also fine from my experience. What is the criteria that can be used for to the quality of model? Does stability alone is enough? Not only stability, it's also about you have to check the other parameters like what to say after if it is a model structure after minimization, check the Ramachandran plot if it is everything is intact and whether the energy has reached a minima or not. Those things can to be carried out. Which one among running MD using single node with multi-thread CPU or running MD using multi-node with multi-thread? Very good question. So keep in mind, if you have a cluster, if it is a InfiniBand, I hope you will understand what is it. InfiniBand means how these nodes are connected. If it is a high-speed InfiniBand, they are fine. Okay, both are fine. But if it is not a high-speed InfiniBand, but you have a single machine is always much faster. Now I have to reframe that question. Multi-thread. So let's say you have i5 machine with you, i5 CPU. In that i5 we say dual core. Dual core means it has only two physical core, but when you open your processing you will see four cores. That means it has two thread also. That is called multi-thread. So one core will have two thread. That makes you to claim that I have four core, right? So sometimes some most of them, not some, most of the MD simulation ab initio algorithms or programs works much better them to run or forcing them to run on multi-thread. So keep that in mind. Certain programs they are fine, but most of the algorithms or codes works much on better on physical code. So if you say two and you have to define that. Now how do we differentiate it? In your BIOS, you have to disable the multi-thread. If you disable it, then software will see only two physical cores. Otherwise, so you have to check with your BIOS. So bit little more technical. Any tools for mesoscale simulation? Yes, there are continuum solvation model, SACs, Unifac, then Cosmotherm. Cosmotherm is paid, unfortunately, but others are free, so you can do, and a few others are also there. How can I learn parameterization from
Yeah,
scratch?
and Giri, sorry to interrupt you. Can you tell us the difference between the normal simulation and the mesoscale simulation? How
I
it
have
differs?
not done mesoscale simulation, so I'm not the
Okay,
right person to comment. Sorry.
okay, okay,
So, but I have read about it when going through the implicit solvation, like the continuum solvation models, and also that
okay.
where I have seen it, where people work on polymers, mixtures, and other things. So
But
I'm
but
not an
you
expert
might
there.
have some idea like where exactly the normal simulation and mesoscale simulation applied, right? Like,
No, that's what I said.
okay,
Mesoscale, I have seen where they are applied on mixtures,
mhm.
polymers, or complexes, where they wanted to extract statistical thermodynamics, as I already mentioned in my slides, like vapor pressure, boiling point. So those kinds of things to extract those parameters. So I'm not an expert in that, so I don't want to give any false comments.
Okay, thank
How
you.
can I learn parameterization from scratch? Can you please make a video on your YouTube channel or a hands-on challenges? How to perform kinetics on simulation? I want to learn essential dynamics. See, parameterization, it's not a simple process. So most of the time, I have seen, even I have also started when I started doing this, we just copy pasted what is there in the tutorial and try to reuse it. Now, when we face problems only, we try to play around by changing the parameters. Now, by reading the manually, we will get to know by changing what value to lower or higher, what is the significance. Otherwise, we will never know from anywhere. No one has written a tutorial very full-fledged in that manner. But the respective softwares have clearly mentioned what is the parameters that you change, what is its significance. If you say from scratch, I would recommend to read the user manual. I know it is a hard job, a boring job, but no other way. Yes, you're right. I'm thinking since 4 5 weeks to make something, but when I saw that it will be like a 4 and 5 hour session, which I don't like, because things should be much short. And if I break the sessions, also continuity won't be there, because in order to do an MD, you need to have 4 or 5 parameterizations, and each one will contain lot of other keywords. So it takes time. So I've never found a solution to cut short the session, so that's why I didn't do it yet. Now, how to perform kinetics on simulation? I really don't know. Are you talking about reaction kinetics or rate, or is that what you're looking for? Then I have not performed any, and I don't know. There are other microkinetics tools available. I don't know what is free. I know paid ones. I really don't want to comment. I want to learn essential dynamics. Can you please reframe that question? I didn't understand what is that essential dynamics. If you can, I can see in your chat. So, Rick, if you can reframe or give a little more detail, it would be good. So let me go to the next slide. By then you can type that particular uh, uh, your question. Why do people use specific MD simulation software for their projects? I don't know. For me, I have tried Amber, I have tried Desmond, I have tried Gromax, I have tried all of them. Now, each one has its own plus and minus. So that's why I always tell everybody, all softwares are equally good and all softwares are equally bad. It is about what is your problem and who is using it. It all depends on that. For your particular problem statement, some software with that specific algorithm suits very well, the other does not. Now, if I say Gromax is the best in this world, and if you follow me, it's a wrong method. Since Giri told I am going to use only Gromax, no, it's very wrong. You have to try for your problem statement. If it is exactly the same, then it's fine. You're also working on 3CL protease, fine. You're also working on similar kind of protease. Then you say, I saw a paper where they have very well written and it is good agreement with experiment. See, ultimately we validate a software when it has a good agreement with the experimental data. If it is not there, then we have to backlog and see if there is something related to that. Otherwise, we cannot say any software that is good or bad. So good and bad, it's all depend upon what is the kind of problem that you have taken and who is going to perform it. If a very no voice person is running it, that software will be bad always, because difficult, you don't get the right answer because you gave a garbage inside. But if an expert is doing it, even on any software, he might be getting good answers, because that's where your initial parameterization should be good. That's why I said any software can be good, any software can be equally bad. So I will not recommend any software. I told you 5 softwares. You are free to use any one of them. All are free. Now you might say it is difficult because I cannot learn all the 4 or 5 of them. Then start with Gromax, because there are plenty of forums, plenty of other things are available, so it is easy for you to ask questions to many people. So that start with Gromax, and then if you see something is not working in Gromax, jump to Amber. That's what is my recommendations. But otherwise, if you're stucking only to Windows, then no choice. NAMD is the only choice. Then you think, no, I want a complete GUI and I need a clickable factor rather than commands and all, then go for Desmond. Desmond comes with a GUI. So it doesn't need any command line. Of course, it has a capability, but it comes with a GUI. So these are the conditions that you can keep in your mind, so that to choose which is the software based on your requirement. But biological problem, unless you give a try, I cannot say which one is good. Okay, so it may depend on the type of molecule, I guess. Exactly what you said. It is the problem. That's what I said. The problem statement. What is the complexity? what kind of parameters you're trying to achieve. I just generalized it rather than telling in empty terms. So it all depends on that which software you want to choose. Then how can I find eigenvalue? And please consider my ignorance. I am very new to. Oh, it's fine, no problem. Eigenvalue. Are you talking about a small molecule or on a larger system? So that's again. So electrostatic calculations and on orbital parameterization on change of positions. Of course, eigenvalues will be calculated. So I can share you some of the details. Yeah, that's what I expected. Ligand, protein ligand complexes. So yeah, so there we do a complex of combination of, because most of the ligand parameterization, the like when you do the topology file, so we talk in the terms of quantum mechanics. That's where the combination comes. So I can share you a few papers which will give you a better idea. Maybe I can share in the group. I know Rick, you are there in the group, so I can share in the group. Is there anything else? Any other questions?
I think there are no further questions.
Okay.
If there is any questions, I think there is no questions. So now,
Okay.
Okay.
yeah, yeah.
So maybe Pranav, thank you so much, and Giri, thank you so much for the wonderful presentation.
No
And,
problem.
and
Thank you.
as you said, we are really happy to host you for the practical session with Jupiter also. So it depends. Like if you are available, we are always happy to host you.
Thank you. Thank you.
Yeah. And
Thank
I
you.
yeah, I request Dr. Mohan sir to give some vote of thanks.
Uh, uh, Thank you, Dr. Girinath. And it is a very good presentation. And even though I'm not a biophysics fan, but I am able to understand some of the dynamics of the molecules based on your presentation. And hope everybody enjoyed that. And especially the earth is started with the physical evolution, then chemical evolution, then biological evolution. Now we are going back from biological molecule to chemical, then to physical evolution, and then see that how best we can combine everything. And it is a teamwork. And when a student is performing a bioinformatics, and as a team, after graduating, what kind of finishing school is necessary for him to concentrate on these molecular dynamics?
Mhm. Okay, so that's a very good question for the students. Anyway, it will give them some insights. Basically, my master's was on bioinformatics, but at the when I passed out from Bharatdasan University, when I passed out, I realized I cannot call myself as a bioinformatician, because when I say bioinformatician, I want to look more into proteomics, a bit of scripting, not bit, a lot of scripting. Some programming is required. That is what the market was expecting from me as a bioinformatician. So I was not good at that time. So what I did is I shift my concentration to molecular modeling, computational chemistry, drug discovery. But when I moved there, we have to realize that there is more of biochemistry, kind of biochemistry, but more of biochemistry chemistry is there. So understanding of organic chemistry and all those things. Now that's where we have to decide. If a student comes out, he has to have an understanding where I should stand. Am I working on something neuroscience or related to completely sequencing, next gen sequencing, or I'm going to switch completely into structure based or ligand based design? Once he makes that decision, then comes the next question. Okay, being very specific to your question, I'm not going to over put everything in general. Molecular dynamics. When you see molecular dynamics, let's say 5 years back in India, I don't think many of them are doing molecular dynamics. Very few, very few. But now, if you ask everybody, everyone is doing molecular dynamics. Now, the question is who is doing in the right way? Maybe still few, not many. Few means within 50s or 60s or 100, not thousands probably. So that's what we have to look at. So students, you have a good future on molecular dynamics, because when I see a lot of openings on postdocs and many others, they do request and ask for molecular dynamics. But the reason, what to say, importance of machine learning and AI somehow made the students to stay back, because they might not be good in Python scripting or programming. but still don't worry, it is very easy to get inside. But molecular dynamics, if you're looking at it, is something very important. Everyone is looking at. So tomorrow's age future will be enzyme engineering, okay, kinetics, then synthetic biology. All these places we require molecular dynamics. We have to simulate it and see. We cannot make
Yes,
them simply on the lab. So there is a good future, but as I said, it is so in my earlier days I used to write in my CV, I know this, but when I go to interview, people will ask advanced questions, then I say I'm a beginner. That is bad. So if you're
okay,
putting mention something on a CV, be confident that I'm ready to answer questions. So
okay.
that what I meant is, indirectly you need to have a deeper understanding of science.
Yes.
That's the expectation.
Sure, sure. For example, if it is a software industry, immediately after engineering, a particular 3 months training is given for a graduate and then ask them to what they want. So like that in bioinformatics, after the graduation, so they may be given some, those who wanted to specialize in that particular field. So an industry and the academia can collaborate and then they can give a just
That is possible.
training.
That is possible. But training centers are there, but I don't know in many of them how far they are going deeper into even what I discussed today. I don't know. Really don't know.
Okay.
I
No,
cannot comment
that is,
anything on that.
besides
So
the training center, I am telling about the real company, what they want to do. So if they train that particular person on that field, so then they will work on that.
sir, you are
So that
very
is
true.
because,
Very true. But
uh,
unfortunately, companies they don't have time. They're working with deadlines.
okay,
So they might not be having a time to teach another person. That's why when
okay,
of most of the time internships, people are still learning, and most of them they are taking their much more efforts. I mean, students are
okay.
putting their efforts
Yes,
more
yes,
into learning things. That is the reason why we cannot blame anybody there. So the best
yes,
part is
yes.
when I was doing bioinformatics, the network speed was just 64 kbps. Now on your
Okay.
mobile, you have something like 16 mbps. So students
Yes.
have access to many things now. They can
Okay.
learn. Only thing we are not dedicating time. Of course, we start doing it, but later, if something is confusing, we lose the interest. So that shouldn't be the case. We have to go on, try, and then you will reach a situation that you have all the basics. Then people will be happy to take you because you have a basic understanding. So they need not to sit and teach you. And later, the industries will get attracted with what you have in your CV. No need of experience, but you need to be able to answer the basic science so that the
Okay.
people will be attracting and they can take you as an intern and you will gradually learn what is the industrial applications of molecular dynamics or any other tool, any other techniques that to be used on industrialization. That is my view, and most of the time it works.
Sure, sure, sure. It is. Thank you so much on behalf of CPMB, TNAU. We are very much thankful to you. Our students are more beneficial, and this is also streaming in YouTube, so they will learn many basic things from your thing, and they will contact you. And I also thank the LLB school, Dr. Magesh and Dr. Pranav and Dr. Divya, and everyone is taking care for educating the good students, and we are very happy, and thank you so much for your illustrious lecture. Okay,
Thank you so
thank
much, sir.
you.
Thank you.
Thank you.
Yeah,
Thank you, everyone.
yeah. Thank
Thank
you.
you. Stay safe. Bye.
Yeah, thank you, everyone. And Pranav, don't forget to say about the feedback.
Yeah, participants are kindly requested to fill the feedback which is shared in the chat. Also, do check our Telegram channel and post your feedbacks there also.
Yeah.
Thank you.
Okay, guys. Thank you so much, and see you everyone tomorrow evening at the same time.
Thank you, Magesh. Thank you.
Yeah. Thank you, sir.
Thank you
Okay.
all.
Yeah.
Bye.
Thank
Bye.
you.